What specific problem does your research address in the context of layer-wise gradient analysis in large language models, LLMs? Can you elaborate on the significance of this problem in existing research?
Our research addresses the lack of understanding regarding the layer-wise gradients in large language models, LLMs, particularly how these gradients scale and distribute across different layers during instruction tuning. Existing research primarily employs probing methods that assess model behavior by observing performance changes when layers are modified or removed, but they do not provide direct insights into the gradients that drive the learning process. This gap in knowledge is significant because understanding the layer-wise gradients can reveal how LLMs perceive training data and align with it, which is crucial for improving model stability and training efficiency. Our study specifically investigates the spectral properties of gradients across different tasks and reasoning paths, highlighting previously unrecognized patterns that could inform better training strategies. By focusing on the gradient behaviors associated with slow versus fast thinking, we provide insights that could enhance the interpretability and effectiveness of LLMs in various applications.
How does the proposed method of analyzing layer-wise gradients work? Please illustrate the process step by step, especially focusing on the techniques like singular value decomposition, SVD, and nuclear norm that you employed.
The proposed method of analyzing layer-wise gradients involves several key steps. First, after the loss calculation and backpropagation in the LLM, we obtain gradient matrices for each projection layer. Query key value and output across all attention layers, denoted as G_QI, G_KI, G_VI, and G_OI. To manage the complexity of these large matrices, we apply singular value decomposition, SVD, which decomposes each gradient matrix into three components, orthogonal matrices U and V, and a diagonal matrix, sigma, containing singular values. We then compute the nuclear norm, defined as the L_1 norm of the singular values, which quantifies the gradient's magnitude and its concentration on the top singular values, reflecting the gradient patterns in each layer. Finally, we analyze the nuclear norms across layers to visualize and quantify the dynamic characteristics of gradients, using metrics like mean absolute difference, MAD, and relative difference, ROD, to assess fluctuations and differences in gradient behaviors across various training conditions.
Can you provide a clear example demonstrating the inner workings of your proposed method? Walk through how gradients are computed for a specific layer using a simple instructional dataset.
In our study, we compute gradients for specific layers of large language models, LLMs, using an instructional dataset represented as tuples of instructions and responses. For instance, consider a dataset sample where the instruction is solve the equation 2x plus 3 equals 7, and the response is x equals 2. After calculating the loss based on the model's output, we perform backpropagation to obtain the gradients for each projection layer, specifically the query, Q, key K, value V, and output O layers. Each gradient matrix, denoted as G_XI for layer I, is then analyzed using singular value decomposition, SVD, to derive its nuclear norm, which quantifies the gradient strength and concentration across layers. By comparing the nuclear norms and their fluctuations across layers, we can observe how the model's learning dynamics are influenced by the instructional dataset, revealing insights into the model's reasoning capabilities and stability during training.
What are the theoretical or practical benefits of using your layer-wise gradient analysis compared to existing interpretability methods for LLMs? What improvements have you observed in stability or training efficiency?
The theoretical benefit of our layer-wise gradient analysis lies in its ability to provide direct insights into the training dynamics of LLMs, particularly through the spectral properties of gradients across different layers, which existing interpretability methods often overlook. By employing metrics such as nuclear norm and singular value decomposition, we can quantitatively assess how gradients behave during instruction tuning, revealing previously unrecognized patterns that inform more efficient training strategies. Practically, our findings indicate that training LLMs for slow thinking, detailed COT, results in more uniform gradient norms across layers, enhancing stability, while fast thinking, simplified non-COT, leads to larger fluctuations and instability. This suggests that incorporating detailed reasoning paths can significantly improve training efficiency by reducing gradient fluctuations and aligning learning more closely with pre-trained knowledge. Overall, our approach not only enhances interpretability, but also contributes to the development of more robust and efficient training methodologies for LLMs.
How did you validate the effectiveness of your method? Describe the experimental design, datasets used, and the metrics you applied to assess performance.
To validate the effectiveness of our method, we conducted experiments focusing on the layer-wise gradients of 5 base LLMs and 5 instruction fine-tuned LLMs across 3 task categories: math, common sense reasoning, and wiki knowledge. We utilized datasets such as Aqua, GSM-8K, and various common sense reasoning datasets, sampling 500 instances for each task to ensure a comprehensive analysis. The experimental design involved comparing gradient behaviors under different conditions, including slow versus fast thinking and correct versus irrelevant responses, while employing metrics like the nuclear norm and mean absolute difference, MAD, to quantify gradient characteristics and fluctuations across layers. Additionally, we analyzed the relative differences in gradient norms to assess how well LLMs could identify irrelevant responses and the impact of instruction tuning on performance. This multifaceted approach allowed us to uncover significant insights into the training dynamics and stability of LLMs.
What results did you achieve in your experiments, particularly regarding the differences in gradient behavior between instruction-tuned and base LLMs? Please provide specific findings related to slow versus fast thinking.
In our experiments, we found that instruction-tuned LLMs did not demonstrate superior capabilities over base LLMs in identifying incorrect reasoning paths, as evidenced by the minor relative differences in gradient behaviors between the two types. Specifically, when analyzing slow versus fast thinking, we observed that training LLMs for slow thinking, detailed COT, resulted in similar gradient norms across different layers, indicating a more stable learning process. In contrast, fast thinking, simplified non-COT, led to larger gradients in earlier layers and significant discrepancies across layers, suggesting instability and fast forgetting. Additionally, when detailed COT paths were provided, the gradient behaviors differed significantly, with larger scales indicating that LLMs could recognize potential conflicts with their internal knowledge, thus requiring more effort to adapt to irrelevant responses. Overall, these findings highlight the importance of detailed reasoning paths in enhancing the training dynamics of LLMs.